What if I told you there's a metabolic pathway built into your body right now that can burn fat without exercise, reverse inflammation without medication, and potentially add years to your life? And what if I told you that modern humans have almost completely lost access to it? Here's the thing. You've been told your whole life that losing weight requires eating less and moving more. That inflammation is just something you manage with pills. That aging is inevitable and unstoppable. But what if all of that is wrong? What if the answer isn't in a pharmacy or a gym, but in something as simple as cold water? Today we're going to explore cold thermogenesis, an ancient survival mechanism that evolution hardwired into every mammal on Earth. We're going to look at the science, examine the evidence, and by the end of this video, you're going to understand why some researchers believe this could be one of the most powerful health interventions available to humans, and the best part, it's completely free. Let's get into it. Before we dive into the biology, I want to tell you how the Western world stumbled onto this pathway, because the story itself reveals just how much we've been missing. Let's start with the Sherpas. For decades, Western climbers have been baffled by the Sherpa people of Nepal. These high-altitude guides don't just tolerate extreme conditions, they thrive in them. While Western mountaineers struggle with altitude sickness, frostbite, and exhaustion, Sherpas carry heavy loads up Everest with what seems like supernatural endurance. Scientists initially assumed this was purely genetic adaptation to high altitude. And yes, Sherpas do have genetic variations that help with oxygen efficiency. But that wasn't the whole story. Researchers discovered that Sherpas have significantly higher levels of brown fat activation than lowland populations. Their bodies are fundamentally better at generating heat and maintaining metabolic efficiency in cold environments. They're not just surviving the cold, they're using it. This wasn't just genetics, this was epigenetic adaptation. Generations of cold exposure had activated pathways that most modern humans have let go dormant. But Western science was slow to connect the dots. Then came the Korean War. In the 1950s, something strange happened on the battlefield. American soldiers were dying from wounds that shouldn't have been fatal. Meanwhile, Korean and Chinese soldiers with similar injuries were surviving at much higher rates. Military doctors were baffled. Same wounds, same severity, completely different outcomes. When they investigated, they discovered something unexpected. The Asian soldiers had been exposed to extreme cold before their injuries. Their bodies had adapted to the cold in ways that made them more resilient to trauma. This observation sat mostly ignored for decades. It didn't fit the existing medical paradigm, so it was filed away as a curiosity. But the Cold War changed everything. Both NASA and the Soviet space program were racing to put humans in the most hostile environment imaginable: space. And they faced the same problems. Astronauts in zero gravity lose bone density and muscle mass at alarming rates. Their metabolisms essentially start breaking down. The cardiovascular system weakens. Immune function deteriorates. NASA researchers began exploring every possible intervention, and they kept coming back to cold exposure. They found that controlled cold could trigger protective mechanisms in the body that nothing else could replicate. Meanwhile, the Russians were conducting their own research. Soviet scientists had been studying cold adaptation since the 1960s, partly because of their climate and partly because of military applications. They documented how cold-adapted soldiers showed improved endurance, faster recovery, and better stress resilience. The Russian research was extensive but largely inaccessible to Western scientists during the Cold War. It wasn't until decades later that this body of work started filtering into mainstream scientific literature. What both space programs discovered independently was that cold exposure wasn't just about surviving low temperatures. It was triggering a completely different metabolic state, one that seemed to protect against multiple forms of physiological stress. But here's where things get really interesting. Around the same time, researchers started studying something called brown adipose tissue or brown fat. For decades, scientists believed that brown fat only existed in human infants. Babies need it to regulate their body temperature because they can't shiver effectively. The assumption was that adults didn't have brown fat. It supposedly disappeared as we grew up. That assumption was completely wrong. In 2009, 3 separate research teams published papers in the New England Journal of Medicine confirming that adult humans do have brown fat. And, not just a little bit, significant deposits primarily around the neck, collarbone, and spine. This discovery connected all the dots: the Sherpas, the Korean War observations, the NASA and Soviet research. They were all pointing to the same thing. Cold wasn't just uncomfortable. Cold was triggering a completely different metabolic state, one that humans had evolved to access but had largely abandoned in our climate-controlled modern world. Now let's talk about what's actually happening in your body when you get cold. And this is where it gets fascinating. Your body has a master hormone that controls your metabolism. It's called leptin. You might have heard of it as the satiety hormone because it tells your brain when you've had enough to eat. But leptin does so much more than that. Leptin is essentially the air traffic controller of your metabolism. It communicates with your hypothalamus, the part of your brain that regulates body temperature, hunger, sleep, and dozens of other critical functions. Here's the problem. Modern humans have become what researchers call leptin resistant. Think of it like this. Leptin is constantly sending signals to your brain. But if those signals come too frequently at the wrong times and in the wrong amounts, your brain starts ignoring them. It's like living next to a train track. Eventually, you stop hearing the trains. When you're leptin resistant, your brain thinks you're starving even when you're not. It thinks you need to conserve energy even when you have plenty stored. It keeps you hungry even after you've eaten more than enough. This is why willpower-based dieting almost never works long-term. You're not fighting a bad habit. You're fighting a hormonal signal that your brain has been programmed to obey for millions of years. So how does cold exposure change this? When your skin temperature drops to around 50 to 55 degrees Fahrenheit, something remarkable happens. Cold receptors in your skin send signals directly to your hypothalamus. And these signals bypass the normal leptin pathway entirely. It's like finding a back door into the control room. The cold tells your brain to switch metabolic programs. Instead of running on the normal warm-adapted pathway that most modern humans are stuck in, your body shifts to an ancient cold-adapted pathway. And on this pathway, everything changes. Your body starts burning fat preferentially. Not because you're restricting calories, not because you're exercising, but because your hypothalamus has received a signal that winter is coming and it needs to access stored energy. Leptin sensitivity begins to restore. Your brain starts hearing those signals again. Hunger normalizes, cravings diminish, and here's what's really wild. This happens without any change in diet or exercise. The cold itself triggers the shift. Let's go deeper into the cellular level, because understanding what happens in your cells explains why cold exposure has such profound effects. Remember that brown fat we talked about? The reason it's brown is because it's packed with mitochondria. Mitochondria are the power plants of your cells. They take nutrients and oxygen and convert them into energy. But here's what makes brown fat special. Normal cells use mitochondria to produce a molecule called ATP, which is basically cellular currency. Your body uses ATP to do everything. Brown fat mitochondria have a different trick. They contain a protein called uncoupling protein 1, or UCP1. This protein essentially short-circuits the normal energy production process. Instead of making ATP, brown fat mitochondria convert energy directly into heat. This is called non-shivering thermogenesis. Your body is generating warmth without muscle contractions, without shivering, just through pure mitochondrial activity. Now here's where it gets really interesting. When you're cold adapted, your body doesn't just activate existing brown fat. It actually converts white fat into something called beige fat. Beige fat has many of the same properties as brown fat. It can burn energy and generate heat. So cold exposure isn't just activating a system, it's transforming your tissue. But there's another piece to this puzzle that most people miss. When your mitochondria produce ATP through the normal pathway, they also produce something called reactive oxygen species, or ROS. These are essentially metabolic exhaust. And in high amounts, they cause oxidative stress, which damages cells and accelerates aging. Here's the thing about the cold adapted pathway. When your brown and beige fat are burning energy for heat instead of ATP production, they produce far less oxidative stress. Let me say that again because it's important. Cold adapted metabolism produces less cellular damage than warm adapted metabolism. This has massive implications for aging. One of the primary theories of why we age is accumulated oxidative damage. If cold adaptation reduces that damage, it could theoretically slow the aging process at the cellular level. And there's research supporting this. Studies on cold-adapted animals show longer telomeres, better stem cell preservation, and extended lifespans compared to their warm-adapted counterparts. We're not just talking about burning fat here. We're talking about fundamentally changing how your cells produce and use energy in ways that could affect how long you live. Now let's talk about inflammation, because this might be the most immediately relevant benefit for most people watching. Chronic inflammation is implicated in almost every modern disease: heart disease, diabetes, Alzheimer's, cancer, autoimmune conditions, depression. The list goes on and on. We live in an inflammatory world. Our food is inflammatory, our stress levels are inflammatory, our sleep deprivation is inflammatory. Even our artificial lighting disrupts circadian rhythms in ways that promote inflammation. Most medical approaches to inflammation involve suppressing it with drugs. And while that can provide relief, it doesn't address the underlying cause. It's like turning off a fire alarm without putting out the fire. Cold exposure works differently. When you expose your body to cold, it triggers a cascade of hormonal responses. Your adrenal glands release hormones like ACTH and cortisol. Your pituitary releases alpha-MSH, which has powerful anti-inflammatory properties. But here's what's fascinating. These aren't suppressing inflammation the way drugs do. They're actually resolving it. There's a difference between suppression and resolution. Suppression means blocking the inflammatory response. Resolution means completing the inflammatory cycle and returning to baseline. Chronic inflammation happens when the resolution phase never completes. Your body stays stuck in an inflammatory state because it never receives the signals to stand down. Cold exposure provides those signals. Studies have shown that regular cold exposure reduces inflammatory markers like C-reactive protein, interleukin-6, and tumor necrosis factor alpha. These aren't small reductions either. Some studies show decreases of 50% or more. And unlike anti-inflammatory drugs, cold exposure doesn't suppress your immune system. It actually enhances it. Cold-adapted individuals show increased immune cell activity and better response to infections. This seems paradoxical until you understand that inflammation and immune function aren't the same thing. You can reduce harmful chronic inflammation while simultaneously improving beneficial immune responses. The cold doesn't weaken your defenses, it optimizes them. Here's where things get weird, and I mean that in the best possible way. Everything we've discussed so far, the fat burning, the leptin sensitivity, the reduced inflammation, these are all consequences of activating what some researchers call the ancient pathway. To understand this, we need to think about evolution. For most of human history, and by most I mean 99.9% of it, Our ancestors lived without climate control. No heating, no air conditioning, no insulated homes. They experienced seasonal temperature variations, cold winters, hot summers. Their bodies adapted to these cycles. And this wasn't just about survival. These temperature variations were information. They told the body what season it was, what food would be available, what metabolic strategy to employ. Winter meant scarcity, so the body would shift to burning stored fat. It would become more efficient. It would activate repair and preservation mechanisms. Summer meant abundance, so the body would shift to growth and reproduction. It would store energy for the coming winter. This seasonal cycling was hardwired into our biology over millions of years. Now think about modern life. We live at 72 degrees year-round. We never experience true cold. We never experience the signals that tell our bodies winter is coming. As far as our ancient biology is concerned, it's eternal summer. And what does the body do in summer? It stores fat. It prioritizes growth over repair. It stays in a metabolically expensive inflammatory state because resources are abundant. We're stuck in summer mode, and our bodies are breaking down because of it. Cold exposure isn't just a health hack, it's a signal. It tells your ancient biology that winter is here, that it's time to switch programs, that it's time to burn fat, reduce inflammation, repair damage, and hunker down. This is why cold exposure has such wide-ranging effects. It's not targeting one system. It's shifting the entire metabolic paradigm. You're not adding something artificial to your body. You're restoring a signal that evolution designed you to receive. The question isn't why does cold exposure work? The question is why would we expect our bodies to function optimally when we've removed one of the most fundamental environmental inputs they evolved to require? Let's get into some of the specific mechanisms. Because understanding the biochemistry helps you appreciate just how profound these changes are. One of the key players in cold adaptation is nitric oxide, specifically a form called endothelial nitric oxide synthase, or ENOS for short. Nitric oxide is a signaling molecule that your blood vessels produce. It causes vasodilation, which means it relaxes and widens your blood vessels. This improves blood flow, reduces blood pressure, and enhances delivery of oxygen and nutrients to tissues. Here's what's interesting about cold exposure. When you first get into cold water, your blood vessels constrict. This is called vasoconstriction. It's your body's immediate response to preserve core temperature by reducing blood flow to the skin. But if you stay in the cold and adapt over time, something different happens. Your body starts producing more ENOS. Your blood vessels become better at dilating. Your circulation actually improves. This seems counterintuitive. Cold makes blood vessels constrict, but cold adaptation makes them dilate better? Yes, and here's why it matters. The ENOS pathway is connected to almost every beneficial effect of cold adaptation. It improves cardiovascular function. It enhances mitochondrial efficiency. It reduces oxidative stress. It even affects how your hypothalamus regulates metabolism. When researchers block ENOS in cold-adapted animals, many of the benefits disappear. The fat burning slows down. The inflammation reduction diminishes. The metabolic improvements reverse. ENOS appears to be a master switch that cold exposure activates. And here's the really fascinating part. The ENOS pathway is ancient. It's found in virtually all mammals. It's part of the original cold adaptation toolkit that evolution built into our ancestors. When you expose yourself to cold regularly, you're not just triggering a stress response. You're activating a sophisticated biochemical system that evolution refined over millions of years specifically to help mammals thrive in cold environments. So how do you actually do this? How do you activate cold thermogenesis safely and effectively? First, let's talk about temperature. The research suggests that skin temperature needs to drop to around 50 to 55 degrees Fahrenheit to trigger the full cold adapted response. This doesn't mean the water or air needs to be that cold. It means your skin temperature needs to reach that range. For most people, water between 50 and 60 degrees will achieve this within a few minutes of immersion. Now here's the important part. You need to adapt gradually. If you've been living in climate-controlled environments your whole life, your cold tolerance is essentially atrophied. Jumping into ice water on day one is not only unpleasant, it can actually be dangerous. The standard protocol looks something like this. Start with cold showers. At the end of your regular shower, turn the water to cold for 30 seconds. Do this for a week, then increase to 60 seconds, then 90 seconds. After a few weeks of cold showers, you can progress to cold water immersion. A bathtub with cold tap water is usually around 60 to 65 degrees depending on your location and season. Start with 5 minutes. Gradually increase duration as you adapt. Eventually, you can add ice to lower the temperature further. But this should come after weeks or months of adaptation, not on day one. There are some important safety considerations. Never do cold immersion alone until you're experienced. The cold shock response can cause gasping and disorientation. Having someone nearby is important, especially early on. If you have cardiovascular conditions, consult a doctor before starting. The vasoconstriction from cold exposure does stress the cardiovascular system, and while this is generally beneficial for healthy people, it could be problematic for those with existing heart conditions. Listen to your body. Shivering is normal and actually beneficial because it generates heat and burns calories. But uncontrollable shaking, confusion, or extreme discomfort are signs to get out. The goal is not to suffer. The goal is to adapt. Consistent moderate exposure is far more effective than occasional extreme exposure. Most practitioners find that after a few weeks of consistent cold exposure, the experience transforms. What once felt unbearable becomes tolerable, then comfortable, and eventually even pleasant. Your body is learning. It's adapting. It's activating systems that have been dormant for years or decades. And once those systems are active, maintaining them becomes much easier. Now let's pump the brakes for a moment, because I always want to give you the full picture, including the limitations and criticisms. The research on cold thermogenesis is promising, but it's not without controversy. First, many of the most dramatic claims come from animal studies. Mice and rats show remarkable responses to cold exposure. But humans aren't mice. Our physiology is similar in many ways, but different in others. Not everything that works in rodents translates to humans. Second, the human studies that do exist are often small and short-term. We have good evidence that cold exposure activates brown fat, reduces certain inflammatory markers, and improves some metabolic parameters. But large-scale, long-term studies are still limited. Third, there's significant individual variation. Some people respond dramatically to cold exposure. Others show minimal changes. Genetics, baseline metabolic health, and other factors all play a role. Fourth, the specific protocols vary widely. Different researchers use different temperatures, durations, and frequencies. This makes it hard to compare studies and determine optimal approaches. And fifth, some of the theoretical frameworks, particularly around evolutionary biology and ancient pathways, are speculative. They're logical and consistent with evidence, but they're not proven in the way that, say, the germ theory of disease is proven. So where does this leave us? I think the honest assessment is this. Cold exposure appears to have real measurable benefits for many people. The mechanisms are plausible and increasingly well understood. The risks, when practiced responsibly, are minimal. But it's not a miracle cure. It's not going to work equally for everyone. And the most dramatic claims should be viewed with appropriate skepticism until more research confirms them. What we can say with confidence is that cold exposure is a tool. It's a powerful tool with a strong biological rationale, and for many people it produces meaningful improvements in metabolic health, inflammation, and overall well-being. Whether it fulfills the most ambitious promises remains to be seen, but the evidence is strong enough that dismissing it would be just as unscientific as accepting it uncritically. Let me zoom out and share what I think is the most important takeaway from all of this. We live in an unprecedented time in human history. For the first time ever, we've created environments that are completely disconnected from the natural signals our bodies evolved to receive. Constant artificial light disrupts our circadian rhythms. Processed food confuses our hunger signals. Climate control eliminates temperature variation. Sedentary lifestyles deprive us of movement our bodies expect, and we wonder why chronic disease is epidemic. Cold thermogenesis is just one piece of a larger puzzle. It's one signal among many that our bodies need but rarely receive. The lesson here isn't just that cold exposure is beneficial. The lesson is that our bodies are designed for an environment that no longer exists. And we have two choices. We can continue living in our artificial bubbles and manage the consequences with medications and interventions. That's a valid choice. Modern medicine has given us remarkable tools for managing chronic disease. Or we can start reintroducing some of the signals our bodies evolved to require. Cold exposure, natural light cycles, movement, real food, connection to nature. This isn't about rejecting modernity. It's about recognizing that our biology hasn't caught up to our technology. And until it does, we might need to bridge the gap intentionally. Cold thermogenesis is one bridge. It's accessible, it's free, and the evidence suggests it's effective. But more than that, it's a reminder. A reminder that your body is not broken, it's not defective, it's not designed to be fat, inflamed, and sick. Your body is an incredibly sophisticated system that evolved over millions of years to thrive. It just needs the right inputs. Maybe it's time to give it what it's been asking for. So there you have it. Cold thermogenesis. An ancient pathway hiding in plain sight. We covered a lot today: the Western discovery of cold adaptation, the leptin connection and metabolic switching, brown fat activation, and mitochondrial efficiency, the inflammation resolution pathway, the evolutionary context, the nitric oxide mechanism, practical application protocols, and the honest, skeptical analysis. If there's one thing I want you to take away, it's this. Your body is not your enemy. It's not working against you. It's working exactly as it was designed to work. It just needs the right signals. Cold exposure might be one of those signals for you, or it might not be. But the only way to find out is to try. Start small. Be consistent. Listen to your body and see what happens. If you found this valuable, do me a favor, hit that subscribe button, drop a comment telling me if you've tried cold exposure or if you're going to start, and share this with someone who might benefit from hearing it. Because here's the thing, this information shouldn't be hidden. Everyone deserves to know what their body is capable of. Until next time, stay curious, stay skeptical, and never stop asking why.